Okay, good morning. All right, so we are studying oscillations, and most of the part of this chapter is covered. Only a small topic is left. Okay, so next we'll see the series and parallel combination of springs. Sorry. All right, so next we'll see the series and parallel combination of springs and change in the time period of a simple pendulum due to the change in acceleration due to gravity. Okay, so that is first of all. Next we'll see the series and parallel combination of springs, and after that we'll talk about the change in the time period of a simple pendulum in various cases. Okay, so suppose there is some acceleration, then what would be the change in time period of a simple pendulum. Okay, so these two parts are left only in this chapter. All right, so let's see this one, the series and parallel combination of springs. So suppose you have the spring and K is its spring constant, right? K is its spring constant. Then this K would be directly proportional to the area of the spring. More is the area, more would be the value of this K, and it's inversely proportional to the length of the spring. Okay, so remember this, that K would be directly proportional to area and K would be inversely proportional to length of the spring, right? Then now suppose you connect two springs in series like this. Okay, and one end of this first spring, it is connected to the rigid support, and the other end of the second spring, it is connected to this mass, and now you exert some force on this. Okay, you exert some force on the system, right? So suppose x1 is displacement in the first spring, x2 is the displacement in the second one. The total displacement, because they are connected in series combination, so total displacement of the mass would be what? X1 plus x2, right? So total displacement is just x1 plus x2, and suppose the k is effective spring constant of these two springs. Okay, so we can say x is equal to F divided by k, right? X is equal to force divided by k. And then now, because you have connected them in series combination, so what will happen? So see here, the force will be equal. Okay, external force is F, right? So the force between this spring and the external force, they will be equal. Okay, so under the equilibrium you can say. So suppose I have stretched this mass. Okay, I stretch it, right, and I hold it. So the force in this direction is suppose F, then this spring will get elongated. Okay, so force in this direction will also be F. Okay, if you just think about this much part, so this mass is there. Okay, one part, sorry, so suppose this mass is there, you you stretch it from this end. Okay, so you pull this mass from this end, not stretch it, you pull the mass from this end, and on other end there is the spring. So the external forces in this direction, the spring forces in this direction, both forces would be equal, right? If you just think of this mass and first spring, or this is actually second spring. Okay, then now here these two springs, if you think about these two springs only, so what will happen here? So if you think of this spring, let's say K2, uh, having spring constant K2, then force on this is in this direction. Okay, and there would be one force due to the other spring also, which is in this direction, and those two forces would be equal and opposite in the equilibrium condition. That means when it is not accelerating, right? Is this thing clear, everyone? Yes, no? Okay, so forces acting on all three would be same. Okay, these three forces would be same. So you can say F is the force with which the mass is pulled. Okay, so force, the spring force, restoring force developed in the second spring, it would also be equal to F. Okay, because this mass is on one end, it is being pulled by this force F, and on the other end, it's the restoring force in this spring, okay, which is pulling that mass in this direction. Okay, so the forces will be equal. So here what you can say is x1 can be written as F by k1, x2 can be written as F by k2. Okay, and that's why suppose Ks is the total spring constant of series combination, then F by Ks is equal to F by K1 plus F by K2, and then you can cancel out F. So what remains is 1 upon Ks is equal to 1 by K1 plus 1 by K2. So if two springs are connected in series, then the effective spring constant is suppose Ks. So what's the relation between K1, K2 and Ks? 1 upon Ks is equal to 1 by K1 plus 1 by K2. And if there are n number of springs, okay, there won't be n springs in the exam, but suppose there are n number of springs, then what would happen? 1 by Ks is equal to 1 by K1 plus 1 by K2, so on and so forth up to 1 upon Kn, right? So this is simple. So this is series combination. Next is the parallel combination. Now in case of parallel combination, see here, this mass is connected to two springs. This is first one, this is second one. Okay, and other end of these two springs is connected to a rigid support. So now you pull this mass with force F. Then now the restoring force in this direction is, suppose in the first spring it is F1, in the second spring it is F2. So this F would be equal to F1 plus F2, right? F would be equal to the sum of F1 plus F2, and therefore you can say that applied force is equal to F1 plus F2. Okay, so therefore now this force can be written as what? We know force is equal to minus k times x. Okay, and F1 can be written as what? Minus of k1 times x. F2 can be written as minus of k2 times x, and the total force can be written as what? Minus of effective k of the parallel combination of two springs, that is kp times x. Okay, and because they are connected in parallel combination, you can see that displacement would also be equal. Okay, both springs would be pulled by the same distance, right? Both springs would be pulled by same distance, so displacement would be equal. So x is same in them, so you can cancel out x, and then you get kp is equal to k1 plus k2, right? Kp is equal to what? K1 plus k2. Is this thing clear? Yes, no? Right? So in series combination, what happens? The resultant spring constant is suppose Ks, then reciprocal of the resultant spring constant is equal to what? Sum of reciprocals of spring constants of all springs connected in series. And in parallel combination, you just have the spring constant is equal to just sum of spring constants. Okay, sum of all spring constants. Okay, that's very simple. Then suppose now the spring is cut, then what will happen? Okay, so here spring is cut. Oh, spring is cut into some parts. Okay, so you have this one spring, and suppose k is its spring constant, so we know that it's directly proportional to area. of cross section and inversely proportional to its length, right? So now if you cut it in the ratio of L1 is to L2 in two parts, then now L1 is to L2 is suppose 2 is to 3, just for an example. So L1 is to L2 is suppose 2 is to 3. So what would be K1 is to K2? Okay, the ratio of spring constants, effective spring constants of the first part and the second part. So here we see that K is what? Inversely proportional to length, right? So since K is inversely proportional to length, then if you want to just compare these two, okay, if you just want to compare these two, K1 and K2, then K1 is to K2 would be just equal to what? L2 is to L1, right? K1 is to K2 would be equal to L2 is to L1, okay? And if you want to compare them with the original spring constant of this spring, okay, then you have K is inversely proportional to L, right? So K is suppose some constant C divided by L. So K1 is equal to C divided by L1 you can say, and K2 is equal to C divided by L2. And then you can, what you can do is you can just divide this K1 by K, and you will get K1 by K is equal to L by L1, right? K1 by K is L by L1 because it's inversely proportional. And similarly, so therefore K1 would be equal to what? L upon L1 times K, and K2 would be equal to L by L2 times K. K1 would be L by L1 times K, K2 would be equal to L by L2 times K, right? So this thing is clear, everyone? Yes, no? Okay. Alright. So now see, spring is cut into two parts and ratio of lengths is suppose 2 is to 3. Then what would be K1? So total length, because ratio of lengths is suppose 2 is to 3. So the length of this part is 2 units, length of this part is 3 units, whatever is the unit, right? And therefore what would be the total length? Total length is 2 plus 3 means 5 units, right? So therefore what would be K1? K1 is equal to 5 by 2 times K, okay? And what would be K2? K2 would be equal to 5 by 3 times K, okay? So because K1 would be equal to what? L divided by L1 times K, right? So L is, total length is 5 units, L1 is what? 2 units, and therefore K1 is 5 by 2 times K, and similarly K2 would be L by L2 times K. So total length is 5, okay, so L is 5 and L2 is what? It is 3 units, so it is 5 by 3 times K, okay? And if you want K1 is to K2, then it would be equal to, if L1 by L2 is 2 by 3, K1 by K2 would be equal to 3 by 2. This is clear? Yes, no? Alright, so here, okay, so now here, now you tell me, so suppose this spring is cut into two parts, the length of first part is 3 units, length of second part is 5 units. So what would be K1 as compared to K? That's simple, right? What would be K1 and what would be K2? Tell me. And here it is cut in two parts. Okay, K1 would be 8 by 3K, right? Because total length is 8 units, okay, and length of first part is 3 units. So K1 would be equal to 8 by 3K. And what about K2? K2 would be equal to what? 8 by 5K, okay, and K1 is to K2. So length is 3 is to 5. Therefore, K1 is to K2 would be equal to what? 5 is to 3. Okay, because L1 is to L2, L1 is to L2 is equal to 3 is to 5, and K and L, they are inversely proportional. So, K1 is to K2 is 5 is to 3. And similarly here, so here you have the ratio of lengths 3 is to 4. So, K1 would be equal to what? So, total length is what? 7 units, right? So, therefore, this is 7 by 3K. K2 would be equal to 7 by 4K, and K1 is to K2 would be equal to 4 is to 3. Okay, so now I guess this is very clear, right, everyone? Okay, so now let's move on to the problems. So two springs of spring constant K1 and K2 are joined in series. The effective spring constant of the combination is given by, tell me. So this is a direct question, right? So you have 1 by Ks is equal to 1 by K1 plus 1 by K2, okay, for series combination. Then this thing can be written as, see here, you will make denominator same, so it will be K1 K2. Okay, you will find LCM of this. So one is this first term is multiplied by what? K2, and second one is multiplied by K1. So this one has to be multiplied by K2 and this one has to be multiplied by K1. So it is K2 plus K1 or K1 plus K2, right? That's 1 by Ks, and therefore what is Ks? So it is K1 K2 divided by K1 plus K2. Okay, so it is option D. Very simple, right? K1 K2 divided by K1 plus K2. Okay, all right, let's see next one. The time period of mass suspended from a spring is T if the spring is cut into 4 equal parts and the same mass is suspended from one of the parts, then the new time period will be. What will be the new time period? Tell me. The spring is cut into 4 equal parts, right? Like this. So, length of one part would be equal to what? L by 4. And suppose initially the spring constant is K, then spring constant of one of the parts, any one of the parts, would be what? It is inversely proportional to length, right? So K prime is suppose K prime is the resultant spring constant of one of the parts. What will be K prime? Length becomes 1/4. So spring constant becomes what? 4 times. Okay. So original spring constant is suppose K. Then the effective spring constant of one of the parts would be what? Any one part would be equal to 4K because length has become 1/4. And then what about the time period? So you can say T is equal to 2 pi square root of m by K, and it is the same mass, right? Okay, same mass is suspended from one of the parts. So T prime would be equal to 2 pi square root of m by K prime. Okay, and you can take ratio of these. So T is inversely proportional to root of K, right? T is inversely proportional to root of K. So T prime by T would be equal to what? Square root of K by K prime, because it's inversely proportional to root of K. So T prime by T would be equal to K by square root of K by K prime. Okay, and K prime is equal to what? 4 times K. Put that. So it is K divided by square root of 4 K divided by 4K. So that K gets cancelled and it's 1 by 2, right? It's square root of 1 by 4 means 1 by 2, and move T on that side. So T prime is equal to T by 2. So that's the answer. Okay, so it is option C. Right, this one is clear. Okay, good. All right, let's see next one. So this is from NEET 17, comparatively what comparatively latest we can say. A spring of force constant K is cut into lengths of ratio 1 is to 2 is to 3. They are connected in series and the new force constant is K prime. Okay, they are connected in series, new force constant is K prime. So then they are connected in parallel and force constant is K double prime. Then K prime to K double prime is, okay. So see, you have a spring and it is cut in the ratio of 1 is to 2 is to 3, right? 1 is to 2 is to 3, and they are connected in series. So see here, now you have cut the spring and you reconnect it. Will there be any change? Will there be any change in the spring constant? You cut it and you connect it back. No, right? So when you connect it in series, what would be the spring constant? So it's K prime. K prime is equal to, or let's write Ks. Ks is equal to K, because spring constant of this whole spring was K. You cut it and again connect it back. Okay, you cut it and connect it back. That means you have not done anything. Okay, maybe you have used some fevistick, but that doesn't matter. Okay, so here we'll not consider whatever material is used for connection, right, for the combination. So it's just combined, right? So Ks would be just equal to K. What about Kp? What about Kp? So total length you can say is 7, right? Then what would be Kp? So this K1, spring constant of this part is K1, of this part is K2, of this part it is K3. Okay, so the spring constant is inversely proportional to length. So therefore total length is what? 1 plus 2 plus 3, 6 units, right? So K1 would be equal to 6 by 1 times of K. K2 would be equal to similarly 6 by 2 times of K, and K3 would be equal to 6 by 3 times of K, right? Whatever it is, this is 6K, this is 3K, and this is 2K. Okay, and what is Kp? So you know Kp is equal to, Kp just equal to what? K1 plus K2 plus K3, and that is 6K plus K2 is what? 2K plus, sorry, it's 3K, 3K, and K3 is 2K plus 2K. Okay, so this is 6 plus 3 plus 2 means 11. So this is 11K, and K is equal to Ks. So you can say 11Ks. And what do you want? You want K prime to K double prime. That means series to parallel. So, okay, what you got is Kp is equal to 11Ks, and therefore what would be Ks is to Kp? 1 is to 11, right? Because Kp equals to 11 Ks. So Ks is to Kp would be 1 is to 11, right? So that's the answer. It's option B. This is clear? Okay, good. Let's see next one. So a mass is suspended separately by two different springs in successive order. Then the time periods is T1 and T2 respectively. So you take a mass, you connect it to two different springs. Then the time period is T1 and T2 respectively. If it is connected by both springs as shown in the figure, then the time period is T0. So now you connect it like this. the correct relation is. What is the correct relation? Okay, so this is again parallel combination, right? This is the parallel combination, and what happens in case of parallel combination? So Kp is just equal to K1 plus K2. Okay, and what's the connection of time period? Time period to the spring constant. So we know time period is equal to 2 pi square root of m by k. So then you can say it is inversely proportional to root of k. Okay, t is inversely proportional to root k, square root of k, or you can say k is inversely proportional to t square, right? You will square this, no? So t square would be inversely proportional to k, or k is inversely proportional to t square. And then when you connect them in parallel combination, then what is the time period? It's t naught. Okay, time period is t naught. So this thing can be written as 1 by t naught square is equal to 1 by t1 square plus 1 by t2 square. Okay, very simple. So it is option B, right? Because 1 by t naught square is t naught raised to minus 2, and that is equal to t1 raised to minus 2 plus t2 raised to minus 2, right? Okay, so this is simple. Alright, let's see next one. Two masses MA and MB are hung from two springs of length LA and LB respectively. They are executing SHM with frequency relation FA is equal to 2FB. They in the relation. Okay. Now these are two strings. These are not springs. Okay. So this is a pendulum, right? A mass connected to a string, right? A mass hung from a string. So then what would be the time period? So time period is just 2 pi square root of L by G. Okay. Does it depend on mass? It does not depend on the mass, right? So option C, option D is incorrect. It does not depend on the mass. Okay, mass that you connect. And then option A is LA is equal to LB by 4. So now out of these two you need to check. Okay. So what's given? The frequency FA is equal to 2 times FB. Alright, so frequency is equal to 1 upon 2 pi square root of G by L. So it's inversely proportional to root of L, right? So FA by FB, FA is equal to what? 2 times of FB, means frequency is inversely proportional to root of L. So here you can say 1 upon, or FA you can write some constant by root of L. Okay, or I will just write 1 by root L because it's inversely proportional to root of L. So 1 upon root LA is equal to 2 times of, here it would be 1 upon root LB. Then we remove the square root. So remove the square root, then what will happen? It will be 1 by LA is equal to 4 times of 1 by LB. Or take that LB on this side, LA on this side. So LB would be equal to 4 times of LA. Okay, LB is equal to LB is equal to 4 times of LA. Okay, or if you want LA, it will be LB divided by 4. So that's the answer, right? So it is option A, LA is equal to LB by 4. Very simple. Right? Okay, good. Let's see next one. A bob of simple pendulum having length L is displaced from mean position to an angular position theta with respect to vertical. If it is released, then the velocity of bob at the equilibrium position. Okay, what would be the velocity of bob at the equilibrium position? So suppose you have this pendulum. So this is the equilibrium position of the pendulum, and it is displaced from mean position at an angle theta. Right. So it is displaced from the mean position at an angle theta. Okay. Right. So then now question is, what would be the velocity of bob at equilibrium position? Tell me, anyone? This angle is theta. Option C, root 2 GL cos theta. Alright, let's check. Okay. So see, you have stretched it, you have pulled it, and you are releasing it, right? So now there is some change in height. Okay, there is some change in height. It's just like as if this bob is released from this much height. What is this height? This height is suppose h. Okay, let's say this height is h. So now this total length would be equal to L, right? And then this length is also L. What can you say? How much is h? So it is this much length minus this much length, you can say. Okay, you want to find out h. So it would be this total length minus this much length. So suppose this length is something, or let's say this is r. Okay, so in this triangle, if you see, what would be r? Or you can say that cos theta is equal to r upon L, and therefore r is equal to L cos theta. And what is h? So L is equal to r plus h. So h is equal to the total length minus r. H is equal to total length L minus r, that is L minus L cos theta. So you got h, and then you know the formula that if something is released from height h, what would be its speed? At the bottom, v is equal to the square root of 2gh, and that is square root of 2g. H is L minus L cos theta, or you can take L common. So if you take L common, so it is L minus 1, L times 1 minus cos theta, right? So it is L times 1 minus cos of theta. So that is the answer. So it is option A. Is this one clear? Right, everyone? Selva Kumar?
Sir, clear, sir.
Okay, good. Let's see next one. Two SHMs with same amplitude and time period when acting together in perpendicular directions with phase difference of pi by 2 give rise to. Tell me. Two SHMs with same amplitude is same, and time period when acting together in perpendicular directions with phase difference of pi by 2 give rise to. Okay, option C, circular motion. Right, that's correct. Okay, that is correct. Alright, so let me explain this. So see here, now here the particle, so suppose this is the particle, it is connected to two springs. One spring is like this, okay, another spring is like this. So its displacement in x direction would be governed by SHM due to this spring, okay, and in y direction it will be governed by SHM due to this one, right? Okay, so now what can you say? Spring constants are same, so x is equal to you can say a times of sine omega t, right? And y is equal to a times of sine of omega t plus pi by 2, because they are saying the phase difference between them is pi by 2. What is this thing? So this is equal to a multiplied by sine of, okay, omega t plus pi by 2, it is cos of pi by 2. Oh, what did I say? Cos of pi by 2. It is cos of omega t, right? Sine of omega t plus pi by 2 is cos omega t. So therefore this is cos of omega t, okay, and x is a sine omega t, y is a cos omega t. You just square it and add it. So if you just square and add it, x square plus y square would be equal to what? A square sine square omega t plus you have a square cos square omega t, and you take a square common, okay. So sine square omega t plus cos square omega t is equal to 1, and therefore you have x square plus y square is equal to a square. This is equation of a circle, right? And that's why it will perform what? Circular motion. Is this thing clear, everyone? Okay, all right, good. I can explain it in different way. So see, if you think of circular motion, so let's consider an object performing circular motion. We know that there is, so suppose there is some object which is performing circular motion, this object, right? So then we know that there is a force acting on it which is along the radius and towards the center, okay. There is a force acting on it which is directed along the radius and towards the center, right? So force acting on it is what? F is equal to what's the formula for centripetal force? I can say F bar is equal to minus of R bar into omega square. Okay, this would be centripetal acceleration times m. Okay, so you have F bar equals to minus of R bar times m omega square. Okay, then you can resolve it along two components. So one would be component in y direction and one would be the component in x direction. So m times omega square is a constant. M is its mass, right? Omega is angular speed, and suppose it's constant in uniform circular motion, right? So then what you can say is Fy would be equal to that constant, this is k, okay. So Fy is just equal to the constant, okay. This is not omega square m by k, this constant is equal to k, suppose, right? So F bar would be equal to what? Minus of k times R bar. So Fy would be equal to minus of k times y, and Fx is equal to minus of k times x. So this is just like this mass is being pulled in x direction with one spring having spring constant k, and in y direction with another spring having spring constant k, right? So x and y are its displacement from this point O in x direction and y direction respectively. Is this thing clear, everyone? Right? Okay, good. So now you just remember this thing because it will take little time to solve it in exam. If two SHMs with same amplitude and same period, okay, same period means k is same, okay, k is equal, right? When acting together in perpendicular directions and if there is a phase difference of pi by 2, then they will give rise to what? A circular motion, okay, they will give rise to a circular motion, right? And if phase difference between them is 0, then what will happen? It will be a linear motion like this. If phase difference between them is 0, then it would be a linear motion, right? It will be motion along a straight line. It will oscillate like this then. Is it clear? Yes, no? Okay. Alright, let's see next one. A mass m Alright, let's see next one. A mass m is vertically suspended from a spring of negligible mass. Okay. A mass m is vertically suspended from a spring of negligible mass. The spring oscillates with a frequency n. What will be the frequency of system if mass of 4m is suspended from the same spring? So this is simple one, right? Tell me. Or actually we have solved this. This is repeated, right? No, it was length. Okay. So frequency is what? It is equal to 1 upon 2 pi square root of k by m. So frequency is inversely proportional to root of mass. Okay. So you can say that f2 is to f1 would be equal to what? Square root of m1 is to m2, and that is equal to, so first mass was m and then you connect mass of 4m, so gets cancelled, so it's square root of 1 by 4, that means 1 by 2. So f2 would be equal to 1 by 2 times f1 or f1 by 2, right? Oh, they have written frequency by n, so it would be equal to, n2 would be equal to what? n1 by 2 or n by 2 you can say. Okay, so it is option A, right? This is simple. Okay, let's see next one. A second pendulum is mounted in a rocket. Its period of oscillation will decrease when rocket is, tell me, moving down with uniform acceleration, moving around the earth in geostationary orbit, moving up with uniform velocity, and moving up with uniform acceleration. Tell me which one is correct? Okay, so see here you have, suppose this is the pendulum and it's inside a rocket. Okay, so first of all, suppose this pendulum, okay, there would be some tension in the string and there would be acceleration due to gravity acting in downwards direction. Okay, so the weight of this bob would act in downwards direction, right? And then if it is moving upwards, what does it mean? That the net upward force is greater compared to net downward force. Net means there is only one force. Tension in the string is greater than mg, right? So T is equal to, or you can say net force. Force is equal to what? So net force is upwards. Let's say it is mass times acceleration. It's equal to T minus mg. And suppose it is accelerating upwards, means T is equal to mg plus ma, or you can say it's equal to m times g plus a. Okay, m times g plus a if acceleration is upwards, right? So then this is the effective value of g. Okay, you can say this is g prime. Okay, this is effective value of g. So effective value of g here is, suppose g prime is equal to g plus a. So if it is accelerating upwards, then effective value of g would increase. If it accelerates downwards, then what would happen? Effective value of g would decrease. Okay, if it is under free fall, then what will happen? Effective value of g would be 0, right? Okay, so effective value of g is g plus a, right? If it accelerates upwards, then it increases. If it accelerates downwards, then it decreases. So now see what will happen. Here we want time period of oscillation to decrease, and you know t is equal to 2 pi square root of L by g. So if g increases, time period would decrease. If g decreases, time period would increase, right? So you want time period to decrease, means g should increase. Okay, so g dash or g prime must be greater than g. Okay, because t prime, time period is decreasing, t prime is less than t, means g prime is greater than g. So what should happen? Should it move upwards or downwards? Tell me now. Or just moving is not enough, it should move with acceleration, right? If it moves with any velocity, okay, even if with the speed of light, right, that's not possible. But suppose hypothetical case, let's consider hypothetical case, it moves with speed of light, still it doesn't matter, right? The time period would remain same according to whatever we have studied. Okay, so moving down with uniform acceleration, if it moves down, then what will happen? G prime would be less than g. Okay, so we don't want this. Moving around the earth in geostationary orbit, so in this case, if it moves in geostationary orbit, then what will happen? Actually g prime would be equal to 0. Okay, moving up with uniform velocity and moving up with uniform acceleration. Uniform velocity is also not correct, this one, right? Moving up with uniform acceleration, this is the answer. This is clear, everyone? Okay, good. Let's see next one. A simple pendulum is suspended from the roof of a trolley which moves in a horizontal direction with an acceleration a. Then the time period is given by. Okay, now tell me. Simple pendulum is in a trolley. Suppose it is in this trolley. Oh, and the trolley is moving horizontally with some acceleration. Okay, so suppose trolley moves in this direction, then what will happen? So that bob of pendulum would feel a pseudo force in the opposite direction, we know that. Okay, and it's equal to what? Mass times acceleration only. So if the bob is being pulled in this direction, okay, by the pseudo force, then it will get inclined like this. Okay, if the pendulum is not oscillating, then it will get inclined, and the pseudo force acting on it, it is given by m times a. Okay, then there is gravitational force acting on it, it is downwards, it is m times g. Okay, so then you can say there is one acceleration due to gravity, one is because of what, the movement of the trolley, right? What would be the effective acceleration or effective acceleration due to gravity? You can say g prime here would be just equal to what, just addition of these two, but it will be vector addition, right? So angle between them is 90 degrees. So therefore g prime would be equal to, I can say, square root of g square plus a square. Is this thing clear? Yes, no? Actually you can say resultant acceleration, they are calling it as a prime. Okay, the g prime, they are calling it as a prime. So that a prime is what, actually it is g prime. Okay, and that's why the answer is what, it is square root of g square plus a square, option D. Okay, all right, so then this thing is clear, everyone? Okay, so now this is the end of this chapter, right? And now within 2 minutes we'll start with the next chapter, that is wave motion. So I am joining back in 2 minutes. Okay.